Hi everyone, this is Shao from Uppsala University, Sweden. This presentation is on word segmentation and morpheme segmentation as sequence labeling. This is the segmentation system that we developed for the shared task in MLP 2017. So this is the outline of my presentation. First, we'll have a general overview of the tasks and also the segmentation system, which is followed by the detailed description of the segmentation model, including the baseline model, the ensemble decoding technique, and also the implementation. Next, we'll have a look at the experiments, including the experimental setup, the data sets, and also more importantly, the experimental results. The presentation will be ended with some conclusions. Word segmentation and morpheme segmentation are both very low level. So they are the initial steps for many higher level natural language processing tasks like post-tagging, parsing, machine translation, etc. Word segmentation can be very non-trivial for languages like Chinese, Japanese, and Vietnamese because there is no clear word delimiters in the surface form. So in this case, actually, word segmentation is very similar to morpheme segmentation, as they can be both regarded as identifying valid boundaries between consecutive characters, and therefore both of them can be viewed as character-level sequence labeling. So in this work, we try to solve both tasks under a single framework by regarding them as character-level sequence labeling. So we adopt the bidirectional recurrent neural networks with conditional random fields as the output interface. So this is a general sequence labeling model and has been applied to many different sequence labeling tasks and also achieves very good accuracy. So our model is completely data-driven with almost no task or language-specific adaptation, and also based on the evaluation results, we can see that the model is very effective and achieves very high accuracies across all the languages. So this is a general overview of the segmentation system. So first, let's take a closer look at the character representations. So in this work, we adopt the concatenated trigram model. So in this example, we have the third character as the pivot character. Its vector representation under this context is the context-free vector of the character itself plus the local bigram and the trigram. So the context-free vector, bigram vector, and trigram vector are all initialized randomly, but they are updated during training by backpropagating the gradients. So now we have the vector representations of the characters, and then we fed them into recurrent layers. We have a forward recurrent layer and a backward recurrent layer. We use the gated recurrent unit as the basic recurrent cell to capture long-term dependencies. So the output of the recurrent layers are fed into the CRF interface. And we apply dropouts to both the input vectors and also the outputs of the recurrent layers. So the CRF interface incorporates the transition information between consecutive precision tags so that the optimal tags over the entire sentence can be obtained. We also have a post-processing step to obtain segmentation results with respect to the tags. So for the CRF interface, while decoding, we can use the Viterbi algorithm to efficiently obtain the position tags Y by the conditional scores S and the transition scores T given the input sequence X. So for word segmentation, we use 4 position tags BIES to indicate a character located at the beginning, the inside, or at the end of a word or as a single character word. For morpheme segmentation, we add an extra tag X for word boundaries. So here we have an example in Finnish. We have the input characters, we have the position tags to be predicted, and also we have the segmentation results that can be obtained with respect to the position tags. So here our approach is a little bit different from some other previous works in which they perform morpheme segmentation at word level. But here we can see that our model is at a sentence level to incorporate information beyond word boundaries for morpheme segmentation. So for ensemble decoding, basically we train 4 models with identical parameter settings with different random seeds. So at the decoding time, both the conditional scores S and the transition scores T are averaged over those 4 models. Our neural networks are implemented using TensorFlow. We adopt the bucket model for GPU acceleration. We also provide implementation of our model, which is available on GitHub. You can use it to reproduce the results reported in the paper, or you can use it as a baseline to compare with your own system. So those are the hyperparameters. Most of them are rather regular, so there's nothing to say about them unless you want to do some re-implementation. So the model is trained for 30 epochs with respect to the performance on the development sets. So for the experiments, we have 3 languages for word segmentation: Chinese, Japanese, and Vietnamese, and also 7 other languages for morpheme segmentation. Basically, we train separate segmentation models for each language. We didn't use any external resources. Later, the evaluation results will be reported in the official evaluation metrics, precision, recall, and F1 score. So for Vietnamese, we use space-delimited units as the basic elements for boundary prediction. But for the other languages, there is no language-specific adjustments. So first, let's have a look at the experimental results on word segmentation. So the scores of the baseline model, the example model, and also some other best performing models of the shared task are presented here. We can see that in general, our model performs quite well. The example model is systematically better than the baseline, but the improvement is rather marginal. It's also interesting to see that actually it achieves very high scores on Japanese in spite of the comparatively smaller training set. This is related to the written system of Japanese, as we know that it's a mix of kanas and Chinese characters, and the switching between different characters can be a strong indicator as word boundaries. Whereas for Chinese and Vietnamese, the system heavily relies on the context. We can somehow see the similar results on morpheme segmentation, as we see that also the ensemble system is better than baseline. But actually, we see that here the scores on Basque and Farsi are substantially lower than the others, and due to the smaller training size. But actually, for Basque and Farsi, we can see that the ensemble decoding is more effective. But in general, we can see that as long as sufficient amounts of training data are available, we can get quite high accuracy on the morpheme segmentation tasks. Okay, so Basically, in this work, we model both word segmentation and morpheme segmentation as character-level sequence labeling. We adapt the bidirectional recurrent neural networks with conditional random fields as the output interface, as the segmentation framework. Our proposed model is completely data-driven, with almost no task or language-specific adaptation. And also, according to the evaluation results, we can say that our model is quite effective for both segmentation tasks. So for some future works, because as mentioned before in the presentation, both segmentation tasks are very low level. So actually the error committed at the segmentation tasks can propagate to higher level tasks. So that even though we can say that the model already performs quite well, but still it's valuable to develop more accurate systems in the future. And also because our approach is supervised and it requires sufficient amounts of data to train them, so in the future we also want to develop some cross-lingual approaches for lower resource languages which don't have enough annotated data. Okay, so that's all. Thank you very much. So if you have questions, you can send me an email. Thank you.